Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
So, Robert, this is episode 4, season 3.
Yep.
We are broadcasting as usual from the campus of the University of North Dakota.
You know, it would be nice to have an unusual broadcast sometime.
So, not on the campus of the University of North Dakota.
Right.
You go on a field trip.
That would be cool.
Let's wait. It would be cold if we go now.
Okay, yeah, you're right.
Let's wait a little bit until we get into the warmer weather.
Let's wait a few months. Yeah.
Then we can do a remote broadcast.
We can try anyway. Yeah.
And we can do it from our car if we had like a connection or something, right? And we're traveling somewhere far.
That's pretty much all you need these days is a connection.
Wait till the summer when we go on actual vacation.
Right.
Then one of us can do it. I'll do that if you like.
Okay.
So I'm going away in June. By the way, I'm just letting you know I'm going away in June on summer vacation.
I'll forget by June.
So I could, dial in by Zoom or something remotely like I did a couple of years back.
Yeah.
And then at some point you should go away on vacation and I can be behind the controls. You'll have to show me what to do.
I'll have to show you what to do.
Still haven't done that.
If
you're sick or incapacitated in some way, this podcast is like done.
Yeah.
You realize that?
I do. And we got to fix that because, there have been a couple of days where it was like, crap, I'm late.
Or I'm not feeling bad, but I got to go because he doesn't know what he's doing.
That happened once.
Yeah. Now, we do have a live chat feature that's running, so if you have any comments or questions related to what we're talking about, that would be great if you could send them in, and we'll address anything that you say.
We will address reasonable comments and questions. I'm going to say that now.
Okay, that's fair.
After last week, I'm going to put that out there.
And also as a disclaimer, so whatever Robert and I say, and we won't get into politics, there's enough on TV that we don't need to.
Right.
Or in the news media, we don't need to address that.
It's just us, folks.
It's just us. So it's our personal opinions and not necessarily the opinions of anyone else or any other thing or any affiliation with the university or whatever.
Yep.
We don't represent anybody
We're
but
representing
ourselves.
only ourselves.
So we're the ones to blame if you hear something that you don't like.
Yep.
Now, to start off this week, I thought I'd once again talk about the comet that recently went by. Atlas, so C/2024 G3 is the official name.
Yeah.
And the way, so you can see the image in front of you. What a beautiful image, Robert.
That's a gorgeous image. I'm jealous.
I think this was taken by Mike White from New Zealand. And at the same time that he took this image of Comet Atlas, there was the Southern Lights. I was going to say Northern Lights. I'm so used to that.
It's the same idea.
It's the Southern Lights, the Aurora Australis, as we would say. So you could see the nice pinkish glow in the sky, and the comet, of course, is in the middle. But then you also see the beautiful reflection on the lake.
Right. And I'm noticing that the star streaks, because you're seeing things further away from the comet, are longer in the reflection.
Yeah, and that's right. So they're not a point.
They're not a point source because you're tracking the comet, not the stars.
That's right. And the other thing too is this for people who live in the South. You're getting lots of beautiful photographs of this comet, but you can't see it from the northern hemisphere, at least not from North Dakota.
Not anymore.
So you don't need to go out and look for it. It's just not there. But hopefully, there'll always be another one. So don't feel sad about it or anything like that. We just got to wait. And just that they're kind of random.
They're kind of that's a good way of putting it. They're random. They're here and then they're gone.
And the only thing we ever worry about, of course, is as long as we don't see the discovery of a new comet that happens to be on one of those trajectories that intercepts the Earth at some point.
That would be a bad day.
That would be a bad day. So you don't want to wish, for a large, fantastic display of a comet if it's on the wrong path.
Right.
So you got to be very careful what you wish for, as they say.
Yeah.
But since we're talking about the Aurora, do you want to say a little bit, maybe, Robert, for those who don't know, where that comes from? Like, what's that related to, that you see this Aurora activity like we see in this image?
Well, there's two things that the Aurora is related to. And one, we've got a whole show on it. We need to have him back.
That's Vincent.
But the main things it's related to is the solar wind and coronal mass ejections, where the sun's blown off material, and the Earth's magnetic field. And it's these solar wind and coronal mass ejection particles following the field lines of Earth's magnetic field and impacting into the atmosphere, the atmospheric gases. And that energizes them, puts the electrons in a higher energy level. And when they fall back, they give off light. And we see that light as the Aurora Borealis or the Aurora Australis.
So the thing to remember then is that the sun is not a static entity.
It is not.
It's very, very dynamic.
Mm-hmm.
Now, it does look static. I'll give that to you. When you do look at the sun on a nice, beautiful, clear day, you can't see anything on its surface with your eyes.
It doesn't look like it's changing, but you know what? It breathes every 6 minutes. It pulsates every 6 minutes.
And with the telescope with the right filters so that you don't damage your eyes, you can literally see the boiling motion, convection on its surface, on the photosphere.
Yep. Granules and supergranules.
So the sun is constantly changing. And along with that, there are certain events that occur once in a while
Right.
that give rise to these type of displays as aurora activity.
Yep.
Now, do you remember the name of the very famous one that happened way back in the 1800s?
Are you referring to the good old Carrington event?
Carrington, 1859, Richard Carrington.
Yep.
So this was a very important event because it was so powerful that at the time, the telegraph communication system that the United States had set up, there was a lot of damage done to that system. A lot of the circuits were overloaded. People reported telegraph poles catching on fire.
Mm-hmm. And I will put it this way. It's the same idea. You can actually listen to the auroras by going out where they're happening and attaching wires, speaker wires, to two different barbed wire fences. And you can hear the auroras. It'll be a radio signal because it's not just generating visible light. It's generating microwaves and radio waves and all this. And you can listen in. And it's the same idea. That field, the Earth's magnetic field shaking from the impact of these charged particles, can induce a current, electrical current, in a stretch of wire.
Now, the Carrington event from the mid-1800s, that was arguably the most powerful solar eruption that we've had since that time.
Right. I think they've recorded one or two that are on that order, but they've been facing away from Earth.
Yeah, I mean ones that would hit the Earth.
Yeah.
Right?
Okay. Yeah.
Because the Carrington event, I'm not just referring to the sunspots on the sun, but of course that interaction with the Earth.
Okay.
So the Carrington event would include telegraph poles catching on fire, people seeing aurora all the way down to Cuba.
Yep.
You know, these kind of extreme events that are very, very unusual. Now, because we haven't had as powerful of that type of event here on Earth since that time, nowadays, compared to the mid-1800s, we have a lot of technology that we base our society on.
Right.
And a lot of that technology includes things that are in orbit around the Earth and beyond even, if you think of observation posts.
And if you induce those types of electric currents in them, boom.
That's the thing. How much damage would we sustain if there was a Carrington event that occurred today
Right.
in 2025?
And I think in the 90s, I heard somebody develop the scenario, and they talked about the fact that at the time there were only, these big transformer zones like we have just down the street from us behind the nice concrete walls. There's only 2 spare of those at the time in the whole U.S. Every one of them would practically every one of them would have been taken out by a Carrington event. And so it's like 30, they estimated it'd be 30 years before we'd recover.
You know, you bring thoughts that one of the things we look out for in terms of our well-being here in the United States is some enemy entity
Right.
letting off a nuclear bomb, not at ground level, but high up in the sky, creating an electromagnetic pulse.
Yep.
An
Good old EMP.
If you ever watched that old movie I think it was from the 1990s called Broken Arrow.
I have.
Yeah, and so that was used in that as well. Or they lit off a small nuclear weapon and caused EMP, right?
And it took out the power grid for a long time.
So imagine that happening today, then if you get that sort of effect, that's equivalent almost to an EMP. That's going to cause so much major damage, and like you said, it's going to take a long time to bring things back to where they are now currently. Right. And satellites in Earth orbit are going to sustain major damage.
Mm-hmm.
In fact, we know that.
We know that.
So the companies who build satellites, at least the ones that are extremely important, and you could put in communication satellites, let's say weather satellites, military satellites, all of these things. There's always wanting to have backup redundancy circuits on board those satellites.
Right.
But we also have spacecraft that are closer to the sun than we are watching the sun.
Yep.
So if an event occurs, we will see the light, of course, here on Earth about 8 1/3 minutes later. But those charged particles, like protons, travel much slower than the speed of light. They could take upwards to a couple of days to reach the Earth. But if they're pointed in the different direction, we don't worry about that.
We don't.
But if they are pointed such that they will intercept the Earth in its orbit at the time they get here, then we do worry about that. And we could give us a heads up, if you like, to say, okay, shut down those satellites in orbit for at least a couple days until the event passes. Of course, you're going to be blind a little bit, but it's better than destroying them completely and have to build new ones and send them up, which could take years to do.
Could take years, yeah. And shoot, there was something I was going to mention in there. I mean, we'll get into studying science later, but if you want to get into a field that people are really working on and excited about, get into solar physics, because one of the key things we're looking for is, how do you predict one of these solar storms? How do you predict and know it's coming before you see anything blasting off the sun?
In fact, we have the terminology for that called space weather.
Space weather.
And there is a lot of money that's available in research grants to study space weather because of the potential tremendous impact on society.
Right. So, I mean, how would you like to be back in the 80s? Not because you wanted to, but because you had to.
Yeah, these are the 1880s, not the 1980s.
Could be the 1880s.
A lot of people would like to be in the 1980s probably, but...
But you know what I mean. Yeah.
Yes, I know what you mean. Now, and the other thing is, how often do these Carrington events occur?
And we're looking at other stars that look like the sun, and apparently they're fairly frequent. We're overdue.
Well, so let's go back in the history of Earth and try to track down when these type of events would occur. Now, there is evidence that this can occur. In fact, a recent paper I noticed that was published in Nature Communication used tree rings to look for the presence of radiocarbon.
Right.
So,
because one of the ways carbon-14 is created is bombardment by these types of particles of nitrogen, and it can produce carbon-14.
So a huge influx of solar protons that hit the Earth, and this paper looked at 2 different epochs of time. One was the year 774, Common Era, so what we would say AD 774, and the other event was in 993. So these are 2 events separated by essentially 200 years.
Right.
That occurred, well over 1,000 years ago. That indicate, roughly 1,000 years ago, that indicated that there were events more energetic than the Carrington event.
There we go. So 200 years between them, and then Carrington event 900 years after that. And, here we are, another 200 years. We're due.
So in 2060 would be, 2059 would be 200 years after the Carrington event.
Okay, yeah.
So here we are in 2025. We're getting close to that.
Yeah.
And our reliance on technology, especially things in space, is going to be even greater and greater.
Right.
By the time we approach that 200 year. Now that's statistics, of course. It could happen tonight.
Could happen.
Right.
The
sun does its thing. And we're sleeping in our beds, and people on the other side of the Earth are using solar telescopes, see a big brightening on the surface of the sun.
Right.
In fact, there's a huge sunspot complex right now on the side facing the Earth that you can read about. And let's say that those group of sunspots then, and 6 hours from now, release a huge amounts of particles heading towards the Earth. Now, if it happens, don't blame Robert and I. This is just one of those.
We're just spitballing here, talking about what can happen.
Yeah, statistically, we don't need. It's not like we have to wait 200 years to say, okay, it's time for one of these things. No, it could happen 30 years before that, or 30 years after that, or any other time.
We would love to have that kind of predictive power, but yeah, good luck.
So what this study is telling us is that events like the Carrington event, and even more energetic than that, has occurred repeatedly in the past. And I don't mean you have to go back 50 million years to see the last event before the Carrington event.
Right.
And there's probably events that may have occurred, between this period of, the year 1000. That's that's the Viking Age, right?
Right.
That
Actually
probably,
it is.
Yeah, there probably was another event that occurred between then and the Carrington event over that span of almost 900 years. And just that we don't have the evidence to show that's the case now, or we haven't found it.
Either we haven't found it, or again, the event happened, but it was aimed away from us.
Yeah, that could possibly be. But
Yeah.
I'm thinking of Carrington events as they actually
That
impact the
impacted.
Earth. Yeah, how
Gotcha.
often are those?
Right.
Yeah, because definitely things that are aimed away would happen way more often than the Carrington event.
Because the sun being a sphere and we are a tiny arc out of the surface of that sphere.
Right. The sun doesn't care where we are in our orbit
No.
around the sun. Right. So it's interesting to know that people are taking this kind of work seriously, maybe more so than we have in the past. And we have better techniques that are more sensitive to this sort of analysis with the carbon-14 detection in these tree rings. So
Well, I was about to say, they can detect it in a particular tree ring now, as opposed to needing the whole tree.
Yeah. So we're getting better and better at that. So that might bring in more of these events we'll realize they've happened.
Absolutely.
I know I've read once that there was an event that happened back in the 1700s in the time when Cook was exploring like the islands of Hawaii.
Okay.
So and
How would
around
he have
that time
noticed
there
it,
was
though?
an event that had occurred, right, from the records.
Okay.
So maybe he reported aurora activity, extreme aurora activity. Right?
Yeah, he was
If you're
down
in
near
Hawaii,
the
that
equator.
would catch your attention. Yeah. So I've read some stuff about that kind of stuff. So I think the Carrington events have happened more often than what we really realize at this point.
We just really didn't start taking note of them until we started having metal wires stretched across the countryside.
Yeah, if it happened in the year 1500, what society would that affect?
Right.
Nowadays, it would throw off our GPS. Everything would go crazy and wonky, right? I mean,
Right.
we talked about this back, the event that happened in May. That threw off the GPS system for farm tractors in Minnesota. So they were reporting problems trying to drive their tractor in very straight lines, right, for tending the fields and stuff. So if that event, which is not even close to being the Carrington-sized event, if that causes problems, what
Imagine
would be
what a
a
big
Carrington
one.
or even larger cause? Well,
Yeah. Hopefully we won't find out, but I'd
it's going to
say
happen.
we're going to find out.
We're going to find out. It's whether or not it happens in your lifetime. That if you're a person listening to this podcast,
Yeah.
I think that's the only thing you have to kind of worry about. But anyways. Now, NASA is going to launch at the end of this month. At least this is when the launch window opens. So, of course, it depends on the weather and all. So this might stretch into March. Is going to launch a new telescope into space called SPHEREx. Now, you might wonder, where does that name come from? Well, the full name or description of this telescope.
Lord.
Do you want to attempt to say that, Robert? It's on the bottom of the slide.
Spectrophotometer for the History of the Universe, Epoch of Reionization, and ICE's Explorer. Wow.
I am clapping. Very good, Robert.
Say that 5 times fast.
Now, this is one of the cases where definitely someone came up with that acronym, SPHEREx, and then said, how can we select words that we could use to spell out that acronym? Right? That's it.
That's
There's
exactly
no
it.
way you would go the other way.
No.
That's too crazy when you think about it. So what is this all about? Well, this is another infrared telescope, and we have one up there now, the James Webb Space Telescope. But the James Webb Space Telescope, when you use it, you're really focused on, no pun intended, or maybe pun is intended here, is focused on a very narrow region of space at a time.
Right.
So
a few milligrees, right?
Yeah, a single exposure, then you're looking at kind of an isolated target. But if you wanted to look at the whole sky, you don't want to wait, and you don't have the time with the James Webb, but if you want to look at the whole sky with James Webb, you're going to wait for a while.
Right.
It's going to take a lot of dedicated pointing to cover the complete sky. And the James Webb wasn't designed for that, but this telescope is. In fact, as you notice there, it has a very large, what we call a field of view.
3.5 degrees by 11. Wow.
Yeah.
Holy cow.
That's extremely large. In fact, that's about, when you multiply that, that's about like 38.5 square degrees per image.
Right. And keep in mind, we've mentioned this before, but keep in mind, a full moon is about half a degree wide.
Yeah.
So, yeah.
Right. So these are 38.5 square degrees. 1 square degree covers about 4 full moons, just a smidgen over 4 full moons.
Right.
So that gives you an idea. If you take 4 multiplied by 38.5, that's the number of full moons you cover roughly, and one exposure, one image.
It's going to cover the sky pretty quick.
Now, one of the things about that is the fact that it has a relatively small aperture telescope. So notice it's only on the order of about 20 centimeters in diameter.
Okay, so for infrared, fairly low resolution.
Yeah, and then that's the trade-off you're getting here, right? And it's one of those class telescopes where you didn't have a large budget, like the James Webb.
Okay.
So you got to keep everything in perspective here.
What is it going to be trying to do?
But the interesting thing here is that this telescope will be able to make measurements over 102 different wavelength bands.
That's impressive.
So that's the photometry. So when photometry in astronomy means you measuring the light of something. So let's say you're measuring the brightness of some star in a particular filter, let's say a blue filter. The act of measuring that light is called photometry. So think of pho and metry, or MERTRY.
Yeah.
It's measuring light is what it breaks down to, that terminology. And so instead of just looking at the brightness of objects in a couple different filters, you look at a bunch of narrowband filters, in this case 102. And so what you're actually measuring is a poor man's spectrum.
I was about to say, this is just not photometry anymore. This is discrete spectroscopy.
Well, that's why it's spectrophotometer.
Spectrophotometer. Discrete, because, yeah, you're getting enough points at that point. You could model a spectrum reasonably easily.
Yes, you're modeling the light output over a huge range of wavelengths, what we call the spectral energy distribution. But these wavelengths are in the infrared. So it's going to tell us a lot about the different properties of galaxies and stars and so on, with very fine measurements in the infrared.
Right. Just not high resolution again. So it will be galaxies and things. It won't be stellar.
And because of the wide field of view, you can look at the whole sky.
Mm-hmm.
So this is an all-sky infrared survey that will take place with all of these measurements per object. And it's going to be amazing.
Yeah.
So it's well worth the amount of money that was spent on this telescope. Like I said, it's a relatively cheap telescope, a small telescope. So you don't break the bank on something like this. But it definitely fills a nice little niche in infrared observations of the universe.
Oh, I would love 102 bands of photometry to have to analyze. Oh, well, yeah, I'd still love it.
Well, we just use AI to do everything now.
Absolutely. Man,
it's a lot easier.
Program up that pipeline.
So we'll see. Hopefully the launch will be successful. It's going up on a SpaceX rocket.
Okay.
And so we'll see how that works. So hopefully everything will be cool. And they release the data. Because if it's a NASA mission, eventually all that data gets released. So scientists like us can grab that data and do some detailed analysis.
I'm going to have to grab some of that data when it starts coming down.
I would love to have that data now for a sample of galaxies I'm currently working on.
Oh, yes, you would, wouldn't you?
That would be very cool. So I can't wait. That'll be interesting.
Absolutely.
Now, to give you an update of a spacecraft that's been up there for quite a while now, this is the Juno spacecraft in orbit around Jupiter.
Mm-hmm.
One of the things that's been reported in the last several weeks is that when Juno flew by Io, one of the moons of Jupiter, this is the most active in terms of volcanoes, most active body in the solar system.
Yep.
And that was a big discovery that was made back in the late 1970s when Voyager 1 flew by Io, that it was noticed that it was volcanoes erupting onto the surface in real time.
Yeah. I mean, at the time, that was phenomenal because we thought Earth was the only geologically active body in the solar system.
Right, and or that the other bodies, it's so rare, when you fly by in a period of just a few days, the chance of you spotting an erupting volcano would be almost zero.
Right.
But that's not the case with this object because it is so active volcanically. That just a random flyby at some random year and some random time and caught volcanoes erupting.
Caught volcanoes.
And that continues even today. So this is an image on the right that you, well, actually there's an image of Io on the left, and that right is the infrared image shown with the circle. In the middle of that circle is an eruption, a very, very powerful eruption that was caught on the surface of Io. And this is a new one. And the area that it comes from is pointed out by that white arrow. So it's at the bottom of Io of the image taken, visible light image taken on the left side. So you can see that part of the Io where that volcano erupted from.
Right. And I'm pointing out that there are several other volcanoes popping off at the same time. Those are other bright spots.
Yeah, you can see the round caldera.
Yeah.
You know, there's one nice in the middle. Almost, I mean, I remember when they first took pictures of it by Voyager, it looks like a pizza. Because of the way that the sulfur and stuff is deposited of the different colors, right? And the different effects of temperature on sulfur itself.
Right.
And the different molecules that you can...
And you can tell, bottom line, what the conditions were when it erupted, what the eruption source material was like, and all sorts of things, simply by the color of sulfur.
And here's a place in the solar system you do not want to buy real estate.
Oh, no.
Because it's constantly changing.
Right.
It's like buying property on Earth. It was lake property when you first bought it and paid the extra money, but now it's no longer a lake. It's just a big lava field or something, right? And not worth anything, right? So
right.
Property values would fluctuate wildly.
I don't know. There's a 3,000 amp current that runs between Io and Jupiter because of this volcanic activity. I don't think I'd want property on Io anyway.
Well, it'd be interesting to note in the future, would we be able to send a lander and touch down on the surface?
It would be interesting. Yeah.
You'd have to be very careful of the electromagnetic interactions that can occur. So only a well-grounded lander.
That was terrible, man.
I'm sorry.
That was bad.
But to think of this volcanic eruption that occurred recently, how much power, went into this volcano? How much did it release? And someone did the calculation, and it comes up with a value equal to about 6 times the amount of energy that's generated by our power plants here on Earth today.
Yeah. That's another thing about the Io volcanoes is they are spectacularly more powerful than volcanoes on Earth. So, Earth's bigger. Of course, its volcanoes are more powerful. Not necessarily.
Yeah, I mean, and the other thing is Io is so close to Jupiter, it only takes like 42 and a half hours to go around once.
Right.
So there's a lot of interaction. I know the sulfur itself is driven out into the orbit of Io. So there's a ring of sulfur going around Jupiter, which is the debris that came off of Io.
Right.
And Io's so close, like I said, it's very short, relatively short orbital period. Remember, it takes the Earth a year to go around the sun. Io to go around Jupiter, 42 and a half hours, right?
Right.
So less than 2 days. So the thing is, it's so close to Jupiter, it really feels there's gravitational tidal forces. And that's what generates essentially the heat that melts the interior of Io that ultimately leads into the volcanic activity that it does have.
And what keeps it its orbit elliptical enough that it does experience tidal effects? The presence of moons like Europa, Ganymede, and Callisto, big moons that are tugging its orbit out of circular, because if it had a circular orbit, they wouldn't experience tidal forces. But because it's highly elliptical due to the effect of these other large moons, it experiences tidal effects and gets squeezed and released.
And that's also related to the presence of life. Because one of the things we like to look for is where possibly would life as we know it be able to exist, let's say on various planets going around different stars in our galaxy and beyond. And so we look for something called the habitability zone. And usually that's defined as where would H2O be in liquid form? In other words, the presence of water.
Right.
If you're too close to the host star, the water boils off to steam, and that's allow you
detrimental.
Or if you're too far away, it gets frozen solid into ice. That's also a negative in terms of supporting life. So there's the sweet spot, the Goldilocks zone, where things are just right.
But thanks to worlds like Io and Europa and Enceladus around Saturn.
Jupiter.
Well, Enceladus is around Saturn.
Oh, I thought you said Io around Saturn.
Io
Yes,
and Europa.
that's right.
We're finding out that we can have liquid water well outside of that Goldilocks zone simply due to tidal interactions around giant planets.
Exactly right. So it expands our notion of where would life be able to arise. The habitability zone now is expanded more. We're looking at different places than what we thought otherwise.
We're also expanding the habitable zone because of things like learning more about atmospheric effects. And so if you have more quote unquote greenhouse gases, you can move a little out of the Goldilocks zone because you're going to retain more of the heat of the star than you would normally expect. So lots of nice things coming up that we are beginning to understand and look at.
And like I said, wouldn't it be nice to have a bunch of nano spacecraft, nano probes, quote unquote,
Yep.
and you release hundreds and hundreds of them, and they go all different places of the solar system looking into these weird locations, right?
Right.
You get some, direct in situ, as we say, measurements of what the conditions are like and so on. Ride along an iceberg in the Saturnian ring system.
Right.
Ride along have it a flotating type of lander that floats along with the lava flow on Io.
Right.
It goes,
could be neat.
Scales down with some type of claws down the crevices of the ice fields of Europa.
Mm-hmm.
So you could think of all kinds of bizarre locations that are tailor-made for our little miniature spacecraft. And ultimately, it would be nice to understand in total what are the conditions like throughout our solar system, because you just never know what happens to the Earth. And in fact, along that line of thinking, there has recently been discovered an asteroid, and it's cataloged as 2024 YR4, which now is at the top of the list for those asteroids that may impact the Earth in the near future.
Mm-hmm.
In fact, this asteroid, which is estimated to have a size somewhere between 40 and 100 meters in width, this asteroid has a 1% chance of hitting the Earth in the year 2032. It's not that far from now when you think about it.
Okay, but we got some time.
We have a little bit of time, relatively speaking.
Yeah.
Now, astronomers and scientists, and of course politicians and everybody else, know that asteroids can be a threat. Did you ever watch the movie Armageddon with Bruce Willis?
I have. I've also watched Deep Impact.
So it's in our pop culture in that sense, right? There's a lot of cheesy sci-fi movies out there that people have made over the years about this kind of stuff. Asteroid or a comet impacting the Earth. Think about the dinosaurs.
Yep.
Think about the event that happened in Siberia back in the early part of the 1900s.
1908.
Yeah. So when you think about those things, then you should be aware that it could potentially happen again. Some large object can hit the Earth. So scientists put together what we call the Torino scale, which runs from 0 to 10, which lists the potential threat of these objects. The larger the number, numeric number, the greater the threat. But right now, this current asteroid, 2024 YR4, is number 3 on that scale, which means that it merits the attention by astronomers.
Right. The thing about asteroids, is, especially this size, is their orbits can be perturbed by the least little thing. So it gets more solar radiation than we expected, and its orbit twists. It passes a little closer to another asteroid, and its orbit gets tweaked. So we need to be watching it. We need to keep track of where it is, what passes near, and how it's moving, because that 1% chance could very suddenly spike to 30.
Yeah, so it's a well-known effect where the sun can heat up one side of an asteroid, even though it's rotating.
Mm-hmm.
And then, and the nighttime side, if you like, it emits those at the heat, the thermal photons, right, infrared photons, and over time that ultimately creates a thrust.
Yeah, because photons, people don't realize it. They may be massless, but they do carry energy, hence momentum.
Right, exactly. And then there is not a net, I should say, it's not like the photons are emitted evenly in all different directions.
Right.
So there is a net force on the asteroid. Even though that force is tiny, over time, that can alter the orbit to a point where if you allow it to continue forward over many, many years, it can be a significant deviation
from what you expect.
From what you'd expect. And so we always have to be on guard for these type of objects, these asteroids, and keep track of them very carefully.
Now, because that thrust is tiny, its effect is greater for small objects than it is for large ones. Ceres has this effect going on, but Ceres is massive enough, it doesn't care that it's got a little tink, 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 tink going on. But this size, over a few years, this can produce a deviation in its orbit.
And it turns out that if this object were to hit the Earth, it would be like the event that happened in Siberia.
It's a city killer.
Yeah. So that's something we have to watch out for. So the chance is pretty low, but if I had a 1% chance of dying and flying in an aircraft, I'd still would worry about that.
I'd still be worried, right?
You'd want that chance to be like way less than 1% if possible, right? 1 out of a million would be a little better.
Would be nice. Yeah.
Not 1 out of 100 like it is here.
Yeah.
So, like this says, it bears the attention by astronomers. So,
right.
But just illustrates this. I mean, this can occur at any random time again. This type of threat. So here we have I guess this is threat day, right? We have that due to the sun and the massive solar eruption that can cause dramatic change to our society. Now we're talking about getting hit by a rock that can flatten a city.
Right.
And hopefully everybody knows it's happening. And the reason for it is all of a sudden a city gets destroyed. Do you want to have some politician think, oh, I think we just got nuked by a certain country, let's retaliate, when it wasn't that at all.
Wasn't that at all, right.
So that's a scary thought.
Yep.
So you have to watch out for that kind of stuff. But, asteroids can certainly destroy life, but they can also bringeth life.
Yep.
And here is a study that was just released recently of a sample of the asteroid Bennu that was taken by the OSIRIS-REx mission. So the OSIRIS-REx collected the sample, brought it back to the Earth, and scientists had a chance now to fully analyze it. And what it shows, not unexpectedly, is that the asteroid contains lots of the raw ingredients from which we think life here on Earth formed. And these consist of different types of molecules, and there's a listing of them on the graphics on the right. There'd be, for example, ammonia, formaldehyde, water is found on there. Also some clays and salt minerals, some precursors that go into the formation of amino acids are found there as well. And so there are lots of sort of chemical type structure that under some presently mysterious conditions, ultimately goes from abiotic to biotic, if you like, right? To go from non-living to living.
And despite what some people think, we do know a lot about this process. We just haven't figured out everything. So this is interesting. This is good stuff. Because even if you don't have DNA and RNA, people don't know this either. But there are other types of self-replicating molecules out there. So this brings back the question, Lane, what is life?
Well, that's it. We kind of talked about that in the past. Obviously, you want something that reproduces. And then we talked about last podcast, something maybe that has a consciousness-like thing.
Yeah.
But then you get down to that rabbit hole. Does a rabbit have conscious?
Right.
And I'm sure it does. A rabbit's got to be conscious of its surrounding. How would it collect food?
Right.
Right? How would it go in a person's backyard looking for, I don't know, tree limbs or something to chew on in the wintertime?
Why would it care about threats if it didn't have some form of self-awareness?
Yeah, but then how far down the chain of life do you go until you reach some entity which does not have that
awareness,
that awareness? Is a blueberry conscious?
Well,
do carrots yell when you pull them out of the ground before you eat them? Do they feel pain?
And they are finding some answers that suggest that yes, they may. So,
Well, we know plants interact with. I've seen studies that even music, that plants have responded to music.
That smell of fresh cut grass is grass trying to releasing chemicals to attract wasps and things like that to attack whatever's attacking it. So plants react to their environment and things that are eating them.
So we haven't
So it's
figured this
crazy.
out.
We
It's
haven't figured it out.
Yeah, it's extremely complex. It's one of the great mysteries when you think about it in biology is where does life actually come from in that. So there's lots of study but that needs to be done. But we do know that some of the basic ingredients
Right.
are seen throughout the solar system. They're on this asteroid Bennu, and we've seen it in other asteroids.
We've seen it on comets.
And we've seen it in comets.
Yeah.
So it's not, as I mentioned, it's not unique to Bennu itself.
It's surprising to see it on what is essentially a lump of rock.
Well, and the other nice thing about it is that we actually went there and scraped up and got a collection, impact the soil with a projectile, and that tossed out that material that was captured by the spacecraft. But that material was collected at the source. It wasn't like a meteorite went through the Earth's atmosphere, landed on Earth, and laid there for many years, contaminated by what's on Earth, and eventually we pick it up and analyze it. And you could always make that argument. Well, these things are just from the fact that the meteorite hit the Earth, and
Right.
it's just contamination from the Earth itself. Here you actually went to the asteroid to pick up the material
Right.
and analyze directly. So it's not being contaminated, hopefully, by the Earth at all, by its environment.
In fact, they went to great pains to make sure it wasn't.
Yeah, I mean, what else you could do is I guess you could intercept the material while you're in orbit in the space station or something and analyze it there.
Right.
And never bring it into the Earth's biosphere at all.
In fact, leave it outside the space station. Work
Yeah.
with it from there.
Yeah, exactly. And people worried about that. Look what they did with the moon landing in Apollo 11, right?
Right.
They kept the astronauts under quarantine for several weeks, scared that there could be some type of biology, some life on that are amongst the dust and soil on the moon that could cause, a major, pandemic, should I say?
Well, we weren't sure that it
COVID.
wouldn't wipe out life entirely.
Yeah, well, that's it, right? And we had no immunity to it. It's like
Right.
War of the Worlds. That's how that goes, right? Where the Martians came and nearly destroyed the Earth until finally earthly bacteria,
Took 'em
viruses
down.
killed them all. Even though we couldn't do it with tanks and our weapons,
And
it
then
was the little creatures that killed them.
and then in the 90s, we retold that story, except this time it was a computer virus.
Yeah. So it's kind of interesting. Then we have the raw ingredients for the formation of life, and it's all over the place. It's not just on the Earth.
Right.
We find it everywhere. And then that begs the question, if we expand our view and think about other planets going around other stars, they would probably have that same ingredient in their system, their solar system. So what's the chance of somehow life arising there? And
Right.
if it's not that probable, right? Let's say it only occurs 1 in a million times in terms of the solar systems. So for every million stars, there's at least one solar system that had life, and this life could be just bacteria or virus-like, very small type of stuff, not like human beings, for example.
Right.
Then there are upwards to 400 billion stars in only our Milky Way, billion with a B.
Yeah.
And if you only need 1 million stars to generate one place where there's life, then look at there's going to be millions of places in our Milky Way that has life. And then there are about 1 trillion galaxies in the known observable universe.
Right. This is why I say if and when we do get out there among the stars, I think we're going to find life everywhere. Intelligent life, I think, is going to be another matter entirely. But that's my opinion.
Well, the numbers become so, I got to say it, Robert, astronomical,
Governmental.
that at some point you also make the argument that there's got to be intelligent life somewhere else, not just on the Earth. But that intelligent life could be on the other side of the Milky Way, or could be in the other galaxy,
Or on
close
the other
to
side
us,
of the universe.
or it could be, or maybe the chance of it happening in one galaxy is like 1.
Right.
So there'll be 1 trillion different places where there's intelligent life, but because they're on average in individual galaxies,
We'll never know.
we'll never know. I mean, it depends in some sense. We'll never know personally.
Okay, yeah.
But the probability of being visited is so low, is so small that the chances is near zero. But not quite zero, but close to it.
Close.
In fact, there is no evidence in the past 4.5 billion year history of the Earth that we have been visited by extraterrestrials.
Right.
And some people claim otherwise, but where's the evidence? Right? Slap the evidence on the table. Show me the muffler of the spacecraft. You see?
I like that.
Or show me the
muffler.
license plate so I can tell where they came from.
Right.
But every time you say that, bring in the evidence, right? Bring in the evidence. Nobody brings in the evidence. Here is a picture. Here's a movie. Oh, my cousin Vinny got a device planted in the back of his head. Well, where's the device? Okay, where's the hardcore evidence?
Right.
Right? We can't just take, people's word for this kind of thing.
We've got Nicholas Williams. Okay, he's agreed with us now. Exactly. Yes. How do you cross interstellar space? That's why I've also made the statement before that if an alien civilization did show up on our doorstep tomorrow, personally, I look at it in terms of what happens when you get two top predators and put them in the same environment. And the answer is one of them goes away. So they crossed interstellar space. I kind of hope they think I'm a neat pet. Because, and some people go, oh, but they'll be so much more advanced. They'll be so much more civilized. How well has that worked for any civilization on Earth?
The other thing is, if you're an advanced civilization, so let's say you formed on a planet around a star, and that star came into existence very early on in the history of the Milky Way, unlike our sun, which came along 4.5 billion years ago, but our galaxy's probably been around for at least 13 billion years.
Right.
So let's say some star formed, I don't know, let's say 10 billion years ago. So they're way ahead of us, right? They're like 5.5 billion years ahead of us in terms of the time available to evolve.
Mm-hmm.
Now let's say some life form then invented space travel, that they could go, based on their engineering, 99.9999999% the speed of light.
Right.
So they would then set out and explore their neighborhood. If we are far enough away from them, they'll never know where we exist, because any external influence that we have caused, which I mean by radio signals or radar signals that have propagated out into space, they've only gone out for, 100 light years roughly.
Right.
So if this civilization is on the other side of the Milky Way, they could be upwards to like 100,000 light years away. They would have to wait 100,000 years for our radar signal to reach them.
And by that time, that signal is so weak, it's lost in the background noise.
Yeah, so there's no way of even knowing. Now, if they are within 100 light years of us, then potentially they could know that we exist.
Right.
But because the chance of advanced life to that point is so small, the chance of them arising nearby that they would know we exist and therefore visit us is also very tiny.
And I will also point out that while we are still using radio communication systems, they're becoming more and more directional. We're also switching to laser systems. So we're going slowly radio dark again, not because we've wiped ourselves out, but because we've got better communication systems that can aim that energy better.
Except for radar. Military radar is what I'm thinking.
Oh, okay.
Right? They're going all the time, right?
Yeah. So I like to put it out that part of that Drake equation is how long are civilizations radio bright? And the answer is it may be just 100 or 150 years, because they eventually go radio dark again, not because they've wiped themselves out, but because they've got better methods that don't require us to blast everything in all directions.
For sure. And to think about, being dinged by a comet, it's kind of like an asteroid. It's the same kind of argument.
Right.
That we got to also keep an eye on those, because those bodies also can get perturbed in the outer solar system. Mm-hmm. In fact, we know Comet Atlas that we just talked about at the beginning of this podcast, that was on a bound orbit, and although it was a very long period comet, but now it's not on a bound orbit because of the gravitational interaction with the sun. It's essentially is on its way out of the solar system, never to return.
Right.
And so there are different comets. In fact, we expect, literally thousands and thousands of comets way beyond Pluto in what we call the Oort cloud.
Yep.
That if the right perturbation occurs, like a nearby passing sun or something, because we are in orbit around the Milky Way, so our position is constantly changing, and we're also oscillating up and down through the galactic plane,
Right.
as well as maintaining our orbit around the Milky Way. So we are passing near other stars and then get further away from other stars, so on. So gravitational perturbations are changing all the time.
Right.
And so if you change it in such a way that causes comets and way out in the solar system to head inwards.
And we don't have to worry about it, but there is, in fact, a star that's supposed to be passing inside the Oort cloud, what we estimate the Oort cloud to be, in the next few tens of thousands of years. So let's see what we got from Nicholas Williams. What likely happens is the data collision occurs in feedback loops of adversarial and an ecosystem that binds them. Right. So he's getting into the whole environmental arguments. And yeah, if aliens showed up, they would have the problem of trying to integrate into our environment. But at the same time, I'm going to lay my money on them doing whatever they want to us because...
You mean like the Borg?
Right, because they crossed interstellar space.
Are they Swedish? That was the joke, right?
Because, somehow they shielded themselves from cosmic rays. They got to a high enough speed that they could make interstellar travel journey reasonably well. Yeah, I'm betting on them.
Now, there is the idea out there that Peter Ward and Brownlee and others who published a book back in the year 2000 called Rare Earth, that you need a lot of different things to go right in order for intelligent life to arise on a planet like the Earth.
Right.
You need a nice stable environment, so it needs a fairly large moon that controls the tilt of the Earth's axis so it doesn't become one extreme to the other. Think of Uranus. Uranus essentially is flipped over.
Yep.
So its rotation axis is in the line of the plane of the solar system rather than being roughly perpendicular to that plane. And so could that happen to the Earth if it... Well, no, because it has a moon that actually causes a stability in the tilt or the extreme range of our Earth's axis. But if we didn't have a moon, then yeah, all bets are off in that sense.
Yep.
And that would have wide changes, potentially impact on our climate. So you need a moon to stabilize things. You need large planets in the solar system that take the brunt of the impacts or redirect objects like asteroids and comets away from the Earth.
Right. And you also need them that they didn't migrate in too close to, so...
And you need metals, right? There's iron in our blood. Where did that iron come from? It wasn't there when the universe first formed. Right? The normal stuff, if you think of the periodic table of elements, was essentially hydrogen, about 74% by mass, and then helium, at roughly 25%, and just a trace amounts of lithium, beryllium, and boron, and that's it. There's no iron. So the iron was forged inside of stars.
Right.
And then stars explode, those massive ones, and blow all that iron atoms out into space that eventually the next generation of stars can form from it. So it builds up the metal content of that material, ultimately giving rise to carbon-based life forms.
Right.
So carbon's not there in the early universe either. That has to be made inside of different generation of stars. So we are, everybody on the planet, think of it this way, everybody on the planet is made from recycled material. Everybody. So do your job and recycle. Reduce, reuse, and whatever the other R is. Right? So yeah. So we need to be in an environment in which we have those atoms that support life as we know it. We can't form right at the very beginning of the universe because there's no carbon. There's no iron. And we need all of those things for life as we know it, for us.
Right.
Now, of course, there can be other forms of life that don't need those type of atoms.
I once made that argument. Show me intelligent hydrogen, and I will concede that there's civilizations that are 13 billion years old.
And the other argument you can make, too, is there are a lot of hostile areas in our Milky Way. For example, near the center. Near the center. Where it's a very high-energy environment.
Near the edge.
So you don't want to be in those areas.
Right.
You probably don't want to be in the center of a globular star cluster. Number one, you wouldn't get any sleep because there's no nighttime.
No nighttime.
It's constantly daylight because there's so many bright stars in the sky. It'd be like daytime all the time. But then you're bombarded by all that radiation, so you have to worry about that effect. And if any of those stars, are very high mass, they go supernova every few million years. and the blast then hits your planet and strips off your atmosphere, then obviously that's an issue.
There we go.
Makes for a bad day.
Makes for a bad day.
So there are only like certain safe regions in the Milky Way that you can be at. So if you take all these factors into consideration, what happens is you can come down to a very low probability that advanced civilization can exist in an individual galaxy like the Milky Way.
Right.
And the Rare Earth book argues that the probability is about 1 for one advanced civilization to occur.
Right. And that's, I will have to agree with that. I don't think we're going to be in a, as much as I love to show a popular science fiction, two popular science fiction franchises that say there's intelligent life everywhere. I don't think that's the case.
And of course, the universe could fool us.
It could.
It could be something we're not quite thinking about. The problem is we're basing all of our arguments on a sample size of 1.
Right.
So, and that makes it very difficult. You're really asking for it if you think that you just go with that. And there's a classic example of that, our own solar system.
I got to admit, I want to be proven wrong, folks. Do not ever get me wrong. Do not ever doubt that. I want to be proven wrong.
Before the first planets going around other stars that other than our own sun, which were discovered in the 1990s, first ones that were around a pulsar, it was thought that solar systems, if they exist, and we didn't know their rarity,
right,
would be just like us. They would have roughly 9 planets. Well, our solar system doesn't even have 9 planets anymore because we got rid of Pluto, right? Remember that?
Well, Pluto's still a planet. It's
just a dwarf planet. But the solar system would be like us. They'd have roughly 4 rocky bodies nearby, and then further out in the solar system, you have 4 gas giants.
Right.
This kind of idea. And that's totally bunk, it turns out. When we started finding planets around other stars, those solar systems were not at all like our solar system.
In fact, I don't think we've found one like ours yet.
We haven't. Doesn't mean it's not out there, of course, but it's just that it seems like the chance, or at least the techniques we have, are very biased. We only find, things that are really massive, really close to the host star. It's much easier to find them. And so the thing is, basing everything on a sample size of 1 is going to get you into a lot of trouble. And then you can use that analogy for life here on Earth. Does life have to be like us? Exactly. Right? Carbon-based life forms and everything that we do and the complex systems that we contain. Is that what every intelligent life would have anywhere in the universe that you look? And you know the answer is absolutely not. It's probably going to be completely different, things that we can't even imagine or think about today.
Yep. I agree.
So if you want to get into these kind of issues, if you want to think about biology, if you want to think about where does life actually come from, very interesting topic. If you want to look around and see what is the potential of life and where would you find it in the universe, in our galaxy and beyond, come to the University of North Dakota.
Yes. You don't even have to endure the cold. You can go online. There's plenty of online programs. Just join us. And if you do decide to brave the cold, come see Wayne and I. We'd love to sit down with you and talk for a while.
Well, Robert, how many places out there that are extremely cold in our solar system and beyond?
Oh, man, there's lots of places colder than we are.
Well, come here and study how life operates in those type of environments.
Good point.
Well, there you go. So we have lots of courses that you can take both on campus and online, as Robert mentioned. And so the important point there is to learn. Even if it's not in any type of STEM field, try to further your education.
Try to learn something.
Try to learn things. Try to learn about what's going on in the world around you. You may be shocked, you may be scared, but it's better than being uninformed because you never know what happens.
Right.
Now, our next podcast will be next Tuesday. So as far as we know, Robert, should we spill the beans? We will have a guest.
We will have
guests. That'll
guests.
be on, so that'll be cool. We'll keep our fingers crossed that everything works out. So that would be on February the 11th.
Mm-hmm.
And we always leave you with a quote at the end of our podcast. This quote, since we talked a lot about gravity in this podcast.
Okay.
Very heavy subject, I understand. And this quote is by Voltaire from 1738. So remember Voltaire?
Okay.
What is he famous for?
No, that's Descartes. I don't remember what Voltaire is.
What unit of measurement do we name after Voltaire?
Is it the volt?
Yes, the volt.
Okay.
So electricity, right?
Yeah.
So anyways, Voltaire, so this is from 1738, and here's the quote. One day in the year 1666, Newton had gone to the country, and seeing the fall of an apple, as his niece told me, led himself to be led into a deep meditation on the cause which thus draws every object along a line whose extension would pass almost through the center of the earth.
Nice.
This is we always learn about Newton, he was underneath an apple tree, an apple comes down, hits him on the head, gravity. He thinks of that right away.
Right.
This is the actual, where that comes from, that story, is from this quote from Voltaire, who spoke to Newton's niece. And it was the niece that told Voltaire that Newton had done this, that he had looked at the falling of an apple and connected to that falling with gravity as being the same thing that allows the moon to orbit the Earth.
Yeah. I got a question too before we go. It was brought up here, and is it Voltaire or Volta?
It's French, so however your French pronunciation is. Voltaire.
Because
Italian.
Voltaire was a philosopher, and that's why you confused me.
Okay.
And Volta was the physicist.
Okay. Maybe that's so.
Okay.
Voltaire. Voltaire.
Okay, so
He's
maybe
the
they
one.
have the same name as the
Maybe.
philosopher.
That could be. I'll have to look that up.
Yes.
He's the one that reported that Newton had witnessed the falling of the apple.
Okay.
That connected what happened terrestrially with what happened extraterrestrially outside
Nice.
of the Earth.
Okay.
That's the genius of Newton.
That was the genius of Newton.
If you do like this podcast, please remember to give us a...
Thumbs up.
I don't see your thumb, Rob.
There it is.
There you go, in case nobody knows what a thumb is. Subscribe if you haven't subscribed. And, of course, thank you very much for listening.
All right. Thank you, folks. Y'all have a great week.